Hello guys, this is Prime Concept. Welcome once again to my channel. In this video, I want to look at a very important aspect of vectors, which is vector differential. So I want to look at the differential part of vector. That is where we'll be talking of differentiation. That is just what it means. And in vector differential, we use a very important operator, which is what we know as the del operator. So this is the major operator we use, the del operator. The del operator is denoted by the symbol. It is denoted by the symbol this. So this is the symbol for the del operator. So this is known as a del operator. That is what we use in vector differential. This is actually known as nabla, right? But that's what we call it in vector is del operator. And it has a formula, right? Yes. The del operator actually is a vector operator that tells us the rate at which a quantity changes in space. It gives us the direction and also the magnitude of that quantity. It gives us the rate at which a quantity changes in space in terms of its magnitude and also its direction. Now, what is the formula for the del operator? The formula is this, which is this over the x. Now, this means partial derivative. So it means we're differentiating partially with respect to x. Then we have our I, let's put it here, plus j, partial derivative with respect to y, and plus k, partial derivative with respect to z. So whenever I see this kind of symbol, this is not the same as d over dx. They are not the same. This means full derivative, while this one means partial derivative, which you would also learn in this video. It's not difficult, trust me. So this is the formula for the del operator. So you can see where I, j, and k are unit vectors that gives us the direction. So it means that the del operator is actually a vector operator because at the end it gives us direction, and then this tells us the rate of change, and then it gives us the direction in which those quantities are facing when they are changing. This is this. Then very quickly we want to look at number one, where the del operator can be applied. It can be applied to what we know as gradient, to obtaining gradients. So we can use del operator in three major applications, or let's say four major applications. Number one is in obtaining gradients, right? Now, and gradient, first point I want you to note about gradient is that gradient is applied to scalars. Gradient is applied to what? Scalars. It is applied to scalars. That's one thing I want you to know. Then, when you apply them to scalars, the second thing I want you to quickly know is that it will give rise to a vector. So it gives rise to a vector. So what we're saying is that the gradient operator are used on scalars. That is one. And then when you use them, the gradient operator gives rise or results to a vector. So what is the symbol for gradient operator? This is how we denote it. Just our del operator together with that scalar, where this is a scalar. So this is what we represent as the gradient operator. So very simple. If we have a scalar, so I can quickly write the full relation to be the gradient of this scalar would simply be I the phi the x plus j the phi the y plus k the phi the z. So this is the gradient operator. Then we want to look at the next one, which is our divergence. Divergence number 2. Divergence. Now, the divergence, I want to also point out important points about divergence. Divergence operates on vectors. It operates on vectors. Very importantly, while we have noted that gradient operates on scalars, divergence operates on vectors, and the result it gives a scalar. So you can see they look opposite. So when it operates on vectors, it would give rise to a what? Scalar. So what does divergence actually tell us? Divergence actually describes the rate of flux at a particular point, the rate at which a quantity flows into a point or flows out of that point. That is what divergence gives us. Now, what is the formula for divergence? It is denoted with this symbol. You'd always see a dot times a, where a is a vector. A is a vector. So this is a symbol for divergence. This dot is what differentiates this from this. In this case, there is nothing. This is just directly attached to this. So that's the difference in their symbols. So take note of that. So the formula is simply going to be divergence of A. Remember, if A is a vector, then this is A. A is AXI, AYJ, and AZK. This is A. If A is a vector, then it means that the divergence of A is simply going to be dx of AX plus dy of AY plus dz of what? AZ. So this is just actually what we do when we do dot product. This is like dot product. So imagine that you are dotting the del operator and a vector. You would notice that the directions would go, because I dot I is 1, j dot j is 1, k dot k is 1. So it's like what we do in dot product. And you will notice that in this final result, you can no longer find I, j, and k. So simply telling you that this result is a scalar, because it does not have directions I, j, and what? K. So it's very important. Then number three is what we know. Number three is what we know as the call. So call is number three. Now, very quickly, I want you to know that call operates. It operates on vectors. Also, it operates on vectors. And second point I want you to know is that it gives rise to a vector. Unlike your divergence operates on vectors and the result is a scalar. But our call operator operates on vectors, but then it gives rise to what? Vectors. These are very important. This can be your exam 100 level questions. Now, what is the symbol? First of all, you should also know that the call operator actually describes the rotation of a system. So it helps you to tell the amount of rotation that a quantity would have. So it describes rotation, rotation about some points. Now we have this is the symbol for the call operator. We use the cross product. Say A is a vector, then this cross is what actually gives the call operator. While for divergence, you see it is a dot. For call, it is a cross product, right? Yes. Now, still using A, vector A, you would notice that your call operator, it's easier whenever you're doing cross product to always use the determinant of the matrix to find it. So I'll do that. The call operator is obtained using determinant of matrix. So I have I, j, and k. Then I have d dx, d dy, then d dz. Then I have ax, ay, and then az. So this is how we can find the call operator. And very quickly, let me just bring out this formula. There's no point, since we'll be solving an example still in this video. We'll be learning how to use this. Then number 4 is what we know as Laplacian operator, Laplacian, right? Yes. The Laplacian operator is actually a scalar operator. It's not a vector, it is a scalar operator. So I want to point out that it is a scalar operator. It is a scalar operator. Unlike our del operator that is a vector operator, the Laplacian is a scalar operator. And when it operates, it usually operates on scalar, even though it can operate on vectors sometimes, but it predominantly operates, it operates on scalars. It operates on scalars. So that is the Laplacian, right? Now, the Laplacian is given by the formula. It's just like double second derivative, this. And then say we have our scalar, where this is a scalar. So these are Laplacian. So you want to write the formula. The Laplacian of a scalar is actually going to be the second derivative of that scalar with respect to x, plus the second derivative of the scalar with respect to y, plus the second derivative of that with respect to what? Z. So this is the Laplacian operator. So very quickly, we want to take a look at one more point. We want to take a look at some key identities that are used or that we can bring out from this, which are very important. And these are where exam questions will be drawn from, your exams, the key identities. So quickly, I'll drop this. Some things that you need to know. What I'm just trying to do is a summary. I'm trying to summarize the vector differential based on demands from students. Some students reached out to me from some universities I won't mention, and then requested for me to solve problems for them under the differential, vector differentials. And I thought it wise to just do a quick summary before I start solving those problems, so that while you're checking those problems, you would really understand from the basic introduction and summary I've done on this. So I don't just want to jump into solving the problems without giving you insight about how these things come about. So that is why I'm doing this summary on vector differential. So key identities I want you to note. Key identities. Number 1, I want you to know that if you have this, say you have a vector, and the core of that vector becomes 0. So if you take the core of a vector and it gives you the result 0, or you say the core of the vector vanishes, that is another way they can use that in exam. So say the core of the vector vanishes. So if you take this and it becomes 0, all it simply means is that it means that the vector field is irrotational. It means that the vector field is what? Irrotational. So very important. Now they can ask you under exam conditions, say find the value of a constant for which the vector field is irrotational. So you should know this. It means it is not rotational, it's irrotational. Number 2, I want you to note if the divergence of a vector also vanishes. If you have a condition where the divergence becomes 0, it means that the vector is solenoidal. It means that the vector is what? Solenoidal. Number three, I want you to also know is that this is always going to be true. Or let's give for Laplacian. So if we have this, if the Laplacian of a scalar also vanishes, then it means that it is harmonic. That scalar is what? Harmonic. So these identities are worthy of note. Number four. Now we can have, these are always going to be true. We can have the divergence of a core. The divergence of a core is always going to be zero, always. And the reason is very simple. This can be proven from our normal vector analysis because we have already established in vectors that the dot product of a cross product, you call this scalar triple actually. So if you have, say, a dot a cross C, or let's say a cross B, this would be zero always, right? And we explain the reason is because this is perpendicular to a cross B. And if two vectors are perpendicular, then you expect that their dot products would be what? Zero. And that is also true for this. So that's why this is always going to be true. Also, I want you to note that the divergence or the core, sorry, should have written this, but let me write this. The core of gradient, that is, I have this plus this. So if you have this, this would always be what again? It would always be zero, right? Then I want to also mention an identity I want you to know. I'll write this as number 6. So we have the identity, this vector triple product cross, we have this cross this. So we have this. This is actually equal to the divergence this is going to be equal to, let me write it here, it's going to be equal to the gradient of divergence, right? Then minus this minus this, the Laplacian, very importantly. So we're going to take some examples now. We're going to take some problems to internalize what we have done so far. I have some problems, so I'll just pause the video and drop the questions so that we can be fast. All right, now we have this question. So we want to tackle it. The question says that this is this. Now you should know that this is actually a scalar. It's a scalar field. How do you know it's a scalar? If you look at the equation given, there is no I, no J, no K. So it means it doesn't have direction. So it means that this is a scalar field. So the question says find the gradient of that scalar field. That is this. So we're looking for gradient. Remember, gradient operates on what? Scalars. Find the gradient at the point D. So what it means is that when we finish finding the gradient, wherever you see x, you substitute 1. Wherever you see y, you substitute -1. Wherever you see z, you substitute what? 2. So we're going to write the formula and then do it one at a time. So we have the gradient formula, which is actually I defy the x plus j defy the y plus k defy the what? Z. So what I'm going to do, I'm going to find the phi, the x first, then I'll find the phi, the y, and so on. Remember, these are partial derivatives. So, and what is our phi? Our phi is this. So what this partial derivative means is that you are differentiating with respect to x. So any other place where you don't find x, it becomes a constant. You throw it away. So let's do this. So if I want to differentiate 2x z square, it means I'm just differentiating x in this case. Z square in this case is a constant, just like 2 is a constant. So now, if you differentiate x to power 1, x, when you differentiate x, you get 1. So it means you have 1 times 2 times z square, you have 2z squared. Because when you differentiate x is 1, you'll be left with 2z squared. So I have 2z squared for this part. If I differentiate this, because I'm also differentiating x and it is 1, then I'll have minus 3y. Minus 3y. And if I differentiate this, because I'm differentiating x is also 1, I would have minus 4. So minus 4. So this is what I have. Very quickly, I'm going to substitute. Wherever I find x, I'll put 1. If I find y, I'll put this. If I find z, I'll put this. So I have 2 into 2 because z is 2, all squared minus 3 into y is minus 1, and minus 4. So if I solve this, I have 2 raised to power 2 is 4, 4 times this is 8, minus 3 times this is plus 3, then minus 4. So I have this minus this is minus 1, 8 minus 1 is 7. So I have this. Next, I want to find the phi dy, just like I did for x. So I'm going to differentiate partially with respect to y. Now, if I come to this first place, because there is no y anywhere, it means when you differentiate this, it will be 0 because it does not contain y. So this would go, it will be 0. Then I come to this place, because I have y to power 1, when I differentiate y, it will give me 1. I'll be left with minus 3x. So minus 3x. Then when I come here, because there is no y, when I differentiate this, it will be 0, right? Then I'm just left with this. So if I substitute, I have minus 3. Remember, x is what? 1. Minus 3 times 1. And my answer is minus what? 3. So also, I want to get the partial derivative with respect to what? With respect to z. So what I'm quickly going to do again is to differentiate this with respect to z. So if I differentiate this first part, because I have z, remember when you differentiate z squared, you would use that 2 to multiply. So I have 2 times 2 is what? 4. Then I have my x. Then I have my z. No power again. Because when you are differentiating, you use the power to multiply. Then you subtract 1 from the power. It becomes z raised to power 1. And once it is power 1, you don't have to write it. Now, if I come to this part, there is no z. So it means if I differentiate this, it will be 0. I come to this part, there is no z. If I differentiate it, it will be 0. So this is what I have. I'm going to substitute now. So I have 4 into x, which is 1, into z, which is 2. So that if I evaluate this, I would have 8. So if I go back, I want to substitute this into this equation so that I have that the gradient operator is going to be my I. What did I get as this? I got this to be 7. This whole thing, we got it to be 7. So it's going to be 7i. 7i. And what did I get as this? I got this to be what? Minus 3 times j. So I have minus 3j. And what did I get as this last part? I got it to be 8. So 8 times k is what? Plus 8k. So it means that my gradient of this is actually 7i minus 3j plus 8k. So I believe this is really very clear to you, right? If you have watched this video up to this point and you are yet to subscribe, please do well to hit the subscribe button, because I'll be dropping a lot of problems from your test, from your CA, from your exams, possible questions. We'll be dropping them. So do well to subscribe, like this video, comment, tell me what next you want me to do, especially those people that sent me this assignment. Tell me what next you want me to do, and I would always make videos on this. So do well to always share with your friends. Now I'll take one more problem, or say 2 more. Once we've looked at gradient, the next we're going to look at divergence, and then possibly look at core from your assignment that you sent. Let's see. All right. Now we have another question, which is a question under divergence. So the question says if A, which is a vector, is equal to this, and how do we know that A is a vector? It carries the direction I and k. There is no j, means the j part is 0. So, but it has I and k, meaning that A is a vector. Now, they said evaluate the divergence. You can see with this dot, you know it's divergence at the point this, meaning that when you finish, you substitute for x 2, for y 1, and for z 2. So we're going to do it gradually also, like we did for our gradient. What's the formula for divergence? Divergence of a vector A is given by the AX, the X, plus the AY, the Y, plus what? The AZ, the Z. So we're going to solve these components one after the other. So I'm going to start with this part. I'm going to bring it out and solve. Then at the end of the day, I'll add it up. So I have D of AX, the X. I want to find this. But before I solve that, I want to quickly let you know. Before we do this. I want to let you know that A subscript X is the part that is connected to I. So the coefficient of I in this case is actually 6x squared y squared z to power 4. This is AX. Now I want to let you know that AY is actually 0 because there's no part carrying J in this case. It means that AY is 0. Then I want to also let you know that AZ is the part connected to K. The coefficient of K is 8x squared y cubed z squared. So these are what we have. So very quickly, we're going to solve these things one after the other. So we're going to find d of the x with respect to ax. So remember, this is a partial derivative. So meaning that we are only interested in x. So looking at this, it means I will just say 2, which is the power of x, times 6. It will give me what? 12. Then I have x. Remember, you're going to subtract 1 from the power. So 2 minus 1 is 1. And you don't have to write the power 1. Once it is power 1, you don't write it again. Then I'll write back y squared z to power 4 because I'm not touching them. I'm differentiating with respect to x. So I don't have to touch these two. That is what I have there. Now, I'm done with this. I'm quickly going to substitute for x, y, and z. Remember, x is 2. So I have 12 into 2. Then my y is 1 squared, then my z is 2 to power 4. So if I do this, I would have 2 to power 2 is 4, 3 is 8, 4 is 16. So 16 times 1 is still 16. 16 times 2 is 32. 32 times 12. 32 times 12 is now going to give me 384. So this is what I have. And the next thing I want to find is d of ay dy. This is actually going to be 0. The reason why it will be 0 is because ay is already 0. So this would be 0. Then the last is d of az dz. So I want to find this, which is this. So I'm going to differentiate just this power. So I have 2, which is the power times 8. It will give me 16. Then I'll write back this x squared. Write back this y cubed. Then I have z. Remember, you subtract 1 from this power. 2 minus 1 is 1. So I don't have to write that 1. So very quickly, I'm going to replace x with 2. So I have 16 into 2 squared. Then y with 1. Then z with 2. So if I do this, I have 2 to power 2 is 4. 4 times this 32 times this 64. So this 64 times this 1, 2, 8. So I have 1, 2, 8. So this is what I have for this. So quickly I'm going to combine in this formula. So my divergence of A is going to be this part, which we got to be what? 384 plus this part, which we got to be what? 0. Then plus this part, which we got to be what? 128. So if I add them up, I would have that's 1, 2, 8. I have 512. So 512. So this is my answer. And what have you noticed? You've noticed that our answer does not carry I, does not carry J, does not carry K. It means that divergence would always give rise to what? A scalar. So I believe it is still very clear to you. So very quickly, I want to look at a core problem so that the three of them will be complete. So let me drop the question. All right. Now I want to look at the last question for this video. I'll be solving more problems in my next video so that this one does not become too long. Now we have if A is equal to this, which is a vector from seeing I, J, and K, you know that A is a vector. Now they said find the core of A at the point this. So I'm going to solve this, is going to be long. We're going to solve it gradually such that you will learn it. Now we have the core of A. This is actually going to be I, J, K. From what we said, we use determinants. So this is going to be D, dx, D, dy, D, dz. And this is AX, AY, AZ. This is what we have. Now, for you to find the determinant of a matrix, you need to know that this would always be plus, minus, and what? Plus. Now, we have, for you to find determinant, when you're considering I, you put I, then you close. So I'm going to do it. You close everything connected to I vertically, and then close horizontally. So if you close this part, like this, and close this part, you notice you have this, 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 this. So how do you get the determinant of this 2 by 2? You just say this times this. So I'll have d az dy minus, when you say this times this, you quickly write your minus, then this times this. So d dz of what? Ay. So this is the first part. And the next part is for your j. Remember, j is minus, so minus j. So I would say minus j. I'll do the same thing. So close everything, every part connected to j like this. I'll close this, and then I'll close the unit vector like this. So if you close this and close this, you would have this, 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 this. So going again, I'll have this times this, which is d az dx. And I'll quickly put my minus. I would say this times this, so which is going to be d ax the what? The z. So this is what I have, but this is not all. I need to get, I'll still add up, but because I don't have space here, I'll write it here. So plus the k part plus k. Open my bracket again. I'll do the same thing. Close for k. I'll close this part. Then I'll close the vectors, the unit vectors. So if I close them, I can find this, 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 and this. So I would quickly say this times this, which is d ay, the what? The x. Then I'll quickly put my minus and go the other way. I'll go this times this, which is d what? Ax of what now? The y. So this is what I have. So then I'm done. So what I want to now do is to actually find this quantity, and this quantity. So you'd see that I have to solve and rub and then continue. And let's start with this. So I need to know what d of a z of this would be. So let's do it one after the other. The a z dy. Let's solve this. So it means I'm going to differentiate az. I'm going to differentiate az with respect to y. Please, what is my az? My az is this part. So if I differentiate this part with respect to y, if you notice there is no y here, it means it's going to be 0. So there's no y, so this will be 0. So same way, I'm going to do d ay with respect to z. So I'm going to look for ay. Ay is the part connected to j, which is this. So I'm going to differentiate this with respect to z. So you can see there is z. So, and if you differentiate z, you get 1. So you'll be left with minus xy squared. So this would give us minus xy squared, because when you differentiate z, it is going to be 1 because the power is 1. Now, I will go to the next one. which is this. So I would say DAZ with respect to what? X. That is this part. I'm going to do them one after the other, then combine it. So this, let's see, where's our AZ? Our AZ is this. Now differentiating this with respect to x, you see I have x. And if you differentiate x, it is 1. So you have 2z to power 4. 2z to power what? 4. Now what I would have done is to be substituting their values. So it will be easy for me. So let me substitute the value of x and y. Remember, x is 4, y is 1. So if I substitute, I have minus 4 into 1 squared. So, and this would actually give me minus 4. So that is this. Remember, this part is 0. So let's do the same. This for this, so that I don't mistake it. Let's do the same for this. So if I substitute this, I'll have 2 into z. Z is 2. 2 raised to power 4. 2 raised to power 4 is 16 times 2 is 32. 32. So I need to find the ax, the z. I need to find this ax, the z. Now very quickly, I'm differentiating ax. This is ax with respect to z. With respect to z. But you'll notice there is no z here, so it means that this is going to be 0. Then I want to do, so I'm done. I think I'm done with this side. I have this, that is 4 of them. I'm done. So I want to come to this side now. So I'll quickly do the ay, the x. Let's see. Now this is ay and x, ay and x. Now let's look for ay. This is ay, there is x. So if you differentiate x, it is 1. So I have minus y squared z. So minus y squared z. So that when I substitute for y is 1. So, and z, I'll have minus 1 squared times z, which is 2. So if I do this, I'll have minus 2. So then I want to also do for the ax dy, which is the last one I'll be doing. So don't mind the work, just because of how big this looks, and I'm trying to even simplify it. So I'm differentiating ax with respect to y. So if I do this, remember this is y squared. So I'll have 2 times 2, which is what? 4. So I have 4x, then y. 4x, then y, because you subtract 1 from this power, it will be 1. So if I substitute, I have 4 into my x is 4, and my y is 1. So if I substitute, I have just 16. So what I'm going to do now, because I'm done, is just to substitute and get my final answer. So to get my final answer, I'm going to have that the core of A, which is what we've gotten, is I into this part, the AZ, the Y. Where is it? The AZ, the Y is 0. 0 minus, I have the AY, the Z. The AY, the Z, I got it as minus 4. So, which is this, let's do it this way, which is minus 4, right? Then next, I have minus J. I'll do the same thing. For my J part, I have the AZ, the X. The AZ, the X, which we got as 32. So it's 32. Then minus, this minus, then the AX, the Z. The AX, the Z is what? 0. So I'll close this. Then finally, I have plus K. K is the AY, the X. The AY, the X, we got it as minus 2. So I have minus 2, then I'll put this minus, which is this. Then I have the AX, the Y. The AX, the Y, we got it as what? 16. So I have this. So if I evaluate this, I would have minus becomes plus 4. 4 times I have 4I. Then the same way, 32 minus 0 is 32. 32 times minus J is minus 32J. Now same way, I have minus 2 minus 16 is minus 18 times this becomes minus 18K. So I've been able to successfully get my what? Core of that vector. So you can see it looks long but very what? Simple. So if you have watched up to this point, thanks for supporting prime concepts. I'll be analyzing a whole lot of concepts in this. I have up to 20 questions under vector differentials. So just to do well to subscribe to this channel, you'll be getting a lot of videos under vectors, physics, maths, chemistry. So share this video with your friends. Tell them to come and check the solution to their assignment problems, their test possible problems, exam possible problems. Tell them to subscribe while they are watching. Keep sharing to your friends. Like, drop comment. The next video you want me to do, drop it in the comment section and I'll attend to it. Thanks for watching my video. It is Prime Concepts.